What I want to talk about today is computer-assisted proofs in the arithmetic of quadratic forms, but not computer-verified proofs, computer-assisted proofs, in the sense of, gosh, there's an awful lot of work here. I wish a computer could help me. So what I wanted to, let's see if this goes right. Okay. So what I want to talk about today is sort of basic background about quadratic forms and classical questions, which are the kind of things I've thought about and written code to try to answer and prove theorems about. Some classical computational questions, a little bit of a local global principle, which is the main technique one uses to approach the arithmetic of quadratic forms. Theta series and modular forms, which I know there's a lot of people who are understand these things very well here, but I'm going to go through a little bit of the background anyway for those who might not. And then how you would determine things algorithmically in terms of representation numbers represented by the quadratic form, associated software, and then the hope that possibly, in conversations with other people, this might one day be formalized. So that's kind of the plan. Cool. So quadratic forms are, a specific type of classical object. There are many different perspectives on them, especially if you go back in the literature. It's a little bit unclear what you should, if you start doing quadratic forms, what you should think of as sort of your fundamental object. So I want to list a couple of possibilities here. And this goes in line with some of the things that Andre and other people were saying about, need to choose a sort of a standard object as you work, right? So the theory of quadratic forms is very old. The literature goes back into the 1800s. People have all sorts of different ideas about what it means, integer valued, integer matrix, things like that, in particular, become kind of hairy. And so you need to sort of really check all the details for yourself. So one definition is sort of quadratic polynomials, where you take a homogeneous degree 2 polynomial and n variables. So that's what you can think of as a quadratic form. And here the coefficients that you write down, the Cij, are given sort of an upper triangular way if you want to sort of write them as a matrix, right? So that's sort of the classical polynomial view. Another view for people who are like linear algebra is sort of the symmetric matrix view. So you can take a quadratic form and you can take the off-diagonal coefficients, the x, xy, xz terms, and you can split them evenly across the ij, ji terms. And so that gives you sort of a symmetric matrix. So it's a matrix A equals A transpose. And you can evaluate that on a vector. And then another perspective on quadratic forms, which is very, very useful, but not as classical, is the perspective of quadratic lattices. So here you think of a quadratic form as being a lattice embedded in a vector space with a fixed quadratic form on it. So you could evaluate this on the lattice, but it's not necessarily presented in the same way. Okay? So we have to make some choices if we're going to start asking questions about the arithmetic of these things. And so the choice I'll make is a quadratic polynomial. This is sort of the simplest thing. And if you're thinking of integrality questions, these different choices really do matter, right? So if you want to say what's defined over z, these different objects defined over z would give you different things.
But this depends on a basis for your vector space.
That's in the third perspective, there's a vector space underlying it, and that's a sort of a fixed basis and a fixed form on that. And you sort of keep that in the background, and then your lattice gets evaluated as however it's presented in the vector space. Yep, that's right. That's right. But so this the quadratic polynomials. You're saying you could change variables, right? Is the idea. Yep. So this leads to the idea of equivalence. So if you have two different quadratic polynomials, you want to say if they're equivalent arithmetically. So you would say that they're equivalent over some ring R. If there is a linear change of variables that's defined over R and invertible over R that takes one to the other. You can also do the same thing for symmetric matrices. So here, there's a, this should be U transpose AU. Two matrices are equivalent over R if there's a change of basis on the quadratic form, which gives U transpose AU. And then quadratic lattices are equivalent over R if you can find an isometry of the vector space that gives you an R module isomorphism preserving values. Okay. So that's kind of the idea. And again, these are slightly different notions, but people tend to pass back and forth between them quite often. One of the things that's useful to notice is that these are actually really not equivalent perspectives. Okay, and so you really have to make a choice. I chose the quadratic polynomials because they really are sort of fundamentally quadratic objects. Symmetric matrices are not the same in characteristic 2, right? You have to divide by 2 when you split things across the diagonal. Okay, and so that's a difference. And a quadratic polynomial you can think of as taking a free lattice in a quadratic vector space, right? And it gives you the representation of the quadratic polynomial. So if it's not free, you can't do that. So the more general notion here is the quadratic lattice, but the more classical notion is the quadratic polynomial.
Okay. Sorry, can you say again, how does the lattice perspective relate to the other?
Yeah, so the idea of the quadratic lattice perspective is you want to think about there's a fixed vector space with a quadratic form on it. And in that vector space, you have a lattice sitting inside embedded. And so when you want to say two lattices are equivalent, you want to say that they look the same in terms of the values that they assume. So you can take one lattice to another with an isometry of the space. Okay?
I guess why is the lattice important here versus just a vector space?
Yeah, because I want to do integral, the arithmetic of quadratic forms. Exactly. Yeah. And it's interesting, I mean, the symmetry groups here are different, right? So the symmetry groups for the quadratic polynomials and the quadratic and the symmetric matrices, this is a GLN type of symmetry. But the symmetry group for the quadratic lattice is an orthogonal group type of symmetry. So it really does lead to different types of results. Great question. Okay, so that's kind of the basics. So we made some choices. And in the classical theory, what you'd like to understand are sort of things about the arithmetic of this, right? So what are things you'd want to know? You want to know things like, what numbers come out, right? You plug integer vectors in, what kind of numbers come out. So what you would say that this is the numbers that are represented by the quadratic form. So if you plug in integers, if your quadratic form has integer coefficients, you get integers out. And in how many ways can you get a given number represented, right? So those are sort of some classical questions. Another thing people ask often is how many equivalence classes are there of quadratic forms? Usually the given determinant. So this comes up in the class groups of binary of quadratic fields. There, the equivalence is a little bit more subtle. It's an SL equivalence, not a GL equivalence, but it's certainly an important thing. And also, you can ask, how does the class number vary as you change D, right? So if you have positive definite forms of higher and higher determinant, you expect them to have more and more classes for a given determinant. And so that kind of asymptotic information and also arithmetic information, and specifically what numbers come out, is very, very useful to understand specific things about quadratic forms. So again, this is a very concrete type of a thing. You have a quadratic form, you want to understand it, right? And that's kind of what's happening here. Okay. So this is values and classes. On the other side, if you think more about sort of the transformations of the quadratic form, there's automorphisms. Okay, so you might want to understand how many automorphisms a given form has, okay? And there are algorithms that allow you to do that for a given form. But in general, understanding how the automorphisms are distributed in the space of quadratic forms is a very useful thing, and it affects the arithmetic quite a bit. And masses is kind of a more formalized notion of automorphisms. This is where you try to understand quadratic forms weighted by 1 over the number of automorphisms, which is kind of a natural thing for many reasons. And so when we think about the classical questions for quadratic forms, just to set the stage, I want to understand values in classes and automorphisms in masses. Okay. Cool. So what kind of things would be interested in doing? Old results about quadratic forms are about when the sum of two squares represents a prime. Right? So you can characterize this in terms of the prime being 2 or a congruence condition. Sum of 3 squares representing a number, an integer, more subtle. This has to do with, this happens if and only if the number is not a power of 4 times something 7 mod 8. Okay? Yep, it's an interesting thing. And also it's non-negative, right? That's important, right? Because squares are positive or non-negative. And then much more simple, the sum of 4 squares, you represent every non-negative integer. Okay? So these are the kind of results that you'd like to be able to understand sort of in general. These are very special. These are sums of squares. So they have a lot of symmetries that helps you to do things. They also have very small determinant, which also helps you to do things. Okay? So this is the kind of prototype. And we would like if our life was always as good as this. And so that's kind of the idea is, well, how could you do this sort of in general? Okay. So some other questions that people are interested in is enumeration of all forms for a given determinant or whose class number is bounded by a certain amount. Okay, so you might find all class number 1 quadratic forms. This is very, very useful in the arithmetic of quadratic forms. And we'll see some applications of that later. In fact, you can see applications of it now because all of these 3 forms here have class number 1. So they're alone in their genus and they're alone in their determinant. And so that means that whenever you want to make a statement, you can sort of make the statement locally, and it'll translate into a global statement. Okay? So this is really, really important. And because this makes your life so easy, you might get a little spoiled thinking that this is always the way it is, but this happens finitely many times. Okay? And so if you really care about questions like this for quadratic forms, you might say to yourself, gosh, how do I deal with class numbers bigger than 1? Right? And that's kind of what I'd like this talk to be about. To talk about how you can think about these kinds of results in a more general setting. Okay, cool. So another question that's kind of classical, goes back to 1800s, but was formalized in the 60s by Katz, is can you hear the shape of a drum? So the idea here is you have a manifold, you want to look at its Laplacian, and you want to understand, can you understand the exact manifold from the eigenvalues on it? Okay. This doesn't a priori look like a question about quadratic forms, but it can be. Because if you look at flat tori, you can make flat tori out of r to the n modulo a lattice, right? And so then the eigenvalues have to do with the values assumed by the quadratic form. And so it turns out that this question was answered explicitly in the context of quadratic forms. Okay. So one thing that was proved, a pretty amazing result, a computational result, I'll mention a little bit more about it if we have time at the end, is that if you would understand the number of ways a number is represented by a ternary quadratic form, a three-variable quadratic form, then this determines the quadratic form up to integer equivalence. Okay? This is not an easy result, and there's no theoretical proof of this. This is a computational result, okay? Done by Shimon in the 90s. Conversely, if you look at four-variable quadratic forms, there are two four-variable quadratic forms that Shimon exhibited that have all the same representation numbers. They represent every number in exactly the same number of ways, but they are not integrally equivalent. Okay? And so these kinds of things are pretty subtle, and they really require a computational mindset to be able to address. Any questions?
Sorry, so the equivalence here is which notion equivalence?
Yeah, it's the notion. It's the notion of equivalence of quadratic polynomials here. But any of them can sort of work in this context because over the integers it's not characteristic too. You can always think of a lattice embedded in a rational vector space. So where we are here, it's kind of all good. But if you start to do things, in local fields and residue fields, and then it becomes more complicated.
Okay.
Yeah. Yeah.
Just to clarify the number of representations, you mean like the function sending an integer to the number of ways it can be represented?
Yeah, so I want to count that if you give me a quadratic form and a number, and I guess I should maybe get to that slide, but if you give me a quadratic form and a number, I want to count the number of vectors I can plug into this quadratic form that evaluate to that number. So it's really the number, it's the preimage of that number under the quadratic map. Yep. Cool. So these are kind of classical questions. And so we want to sort of try to formalize them as best we can and think about how we can sort of try to generalize these things. Okay, so I kind of got involved in this game because I like quadratic forms. I was involved with masses of quadratic forms, orthogonal groups as a graduate student, and I was looking for the next thing to do, and I wasn't really sure. And I read this great article by Bill Duke in the notices where he talked about numbers represented by quadratic forms and that people really understood these things in principle for 5 or more variables and maybe for 4 variables. I mean, there's a general theory, but nobody really knew the actual answer. They're like, here's the form of the answer for sufficiently large things or in general. I said, gosh, why don't we find the actual answer? I like sort of terminal theorems where there's really nothing more to say, right? And so in this case, what I wanted to try to do is to answer this question in a context where we could apply other tools to be able to get a sort of a simple answer. And that's kind of what I want to talk about now. So here are some examples. So we already talked about the sum of 4 squares. So if you want to know what numbers it represents, what values come out of it when you plug in integer vectors, we know it represents all non-negative integers. Okay? And there are lots of ways that we understand that proof. But if I ask you a question about a very similar looking quadratic form, so x squared plus 3y squared plus 5z squared plus 7w squared, which is diagonal, it looks pretty simple, has a lot of symmetries, right? You can sort of imagine them when you're doing this. The conjecture was that this represents all non-negative integers except for 2 and 22. And so the reason this is interesting is a conjecture by, Knaze or popularized by Kaplansky, is that there was no way using the existing techniques of quadratic forms, which are essentially class number 1 techniques. You have a local global thing in some situation, you try to embed it into the thing you care about, they were not able to answer this question. Okay. So the idea is to try to sort of answer this or prove this theorem, and we can sort of talk about how that works. And in general, the answer to these types of things, if you have a positive definite integer valued quadratic form, so something like a quadratic polynomial of integer coefficients that represents only non-negative values, and represents 0 exactly once, then you know that if your number is sufficiently large that you want to represent, and there's no local obstruction, so congruentially there's no problem with representing it, then you know that it is represented. Okay? So this is a theorem by Tartakovsky, I think in the 30s, using the circle method. Okay, so this is sort of the idea here is there's a main term and there's an error term, and the main term is strong enough in this case that eventually it wins. If you decrease the number of variables, the problem gets harder, and you get more features in terms of what you see. And you can actually go down to n equals 3 and make a statement, and n equals 2 is really kind of arithmetic, has class field theory. Okay, so there's really not an asymptotic thing going on. But there's the bounds, the error term bounds were improved sufficiently by Kloosterman that he was able to handle the case when n equals 4. So the main term gets weaker and weaker as you decrease the number of variables. And that makes sense because you have a large dimensional space mapping onto a line, right? The bigger your dimension is, the more things map onto it, the stronger your sort of local terms are. Okay. And so here, if you have a quadratic form in 4 variables, and then if the numbers are sufficiently large, but they're large by not growing at a certain finite set of primes. So they might have like a prime 2. Powers of 2 might allow your number to grow. But if you do that for some quadratic forms and some primes, that won't actually grow your main term. Okay, and that's kind of the idea here. So the prototypical answer, and if you're satisfied with this, then we can end the talk, is that this is how quadratic forms behave, right? So that's the answer to your question. Okay, but this is not quite the same as the statement above. It represents everything but 2 and 22, right? And so the work would be to sort of how do you get from something down here, the sort of general answer, to something up here, which is very explicit and has no uncertainty in it. Yeah?
In the previous slide, you said that number of representations determine in the 3 variable case determines the quadratic form uniquely.
Yes.
So, right?
The class.
So here, what is meant is that the array of integers of like for every I in the natural numbers, the number of pre-images of that quadratic, of that I in the quadratic. So it's like,
yep.
So it's not like, so it's a massive amount of data.
Yep.
It's not like one number.
That's right. Yeah, yeah. So this is the full sort of cardinality of all the level sets of the quadratic forms on the integers. Exactly. Yeah, as a list, right? And we'll make that list more explicit and do things with it. But yeah, that's the data going in. Yep. Cool. Any questions? Okay. Cool. So that's kind of the idea. So we'd like to be able to make this more explicit. Okay. So the nice thing is that when you look at this, they kind of look like these are similar problems. And if you try to do it, you realize they're very, very different. So this top, I don't know how many people know proofs of sums of four squares, but there are many, many proofs, right? There's proofs by geometry of numbers, quaternion algebras, the class number thing, class number 1, like I mentioned before, was discovered through elliptic functions and some explicit formulas there. So it's just like everywhere dense. So if you want to sort of learn number theory, one way to do it is to sort of say, how many ways can I prove the sum of 4 squares represents all natural numbers, right? And you learn an awful lot of number theory that way. Okay. But in contrast, this very similar looking form only has one very long, very computational proof. Okay. And so maybe as a sort of show my cards ahead of time, so one thing I would be really excited about is to make this a formally verified proof. Okay. And so I've learned a little bit about sort of what one can do with these formal verification systems, and I'm super excited as to how quickly things are growing in the database. And so as I'm going through this, sort of the idea is to showcase maybe here the elements of the proof and what could you do to formalize it. Right? So it's a question, an open question to you, but I'm happy to answer any questions you have. Okay, thanks. All right, so the idea behind how you approach a lot of questions in number theory, including things with quadratic forms, particularly quadratic forms, is a general local global principle. Okay, so the idea here is you want to understand something about the integers, in this case, the arithmetic of quadratic forms, something about numbers represented by integers, and you want to understand things in terms of what's happening locally, and then try to put that together and get some global information. Okay, so you always know the global local principle, because you can always take an integer and reduce it mod powers of p, embed it p-adically, or look over the real numbers. So that's good. And so that gives you sort of necessary conditions to be represented, and that's the obstructions we saw before, the congruential obstructions. But what you'd really like to be able to do is to go the opposite direction. So let's say I know I have a number locally everywhere, at every power of mod every power of a prime, and over the real numbers, there is a solution vector x in that system that gives you the image of this integer. Then can you find an integral vector that does this?
Is ZP the integers mod p or the p-adic integers?
The p-adic integers. Yeah, so I could have equally... Say again?
I didn't
Okay.
say.
Yeah, okay. The p-adic integers, exactly. Yeah. So the question you really want to ask is, what's the most explicit form of a local global principle you have for quadratic forms, right? Because to do this kind of thing, you want to be able to really make precise these sort of asymptotic statements, and so you want to use the strongest theorems that you have. Okay? So you may have seen also local principles in the context of quadratic forms, the Hasse-Minkowski theorem. So this tells you about sort of representing things rationally, if you can represent it over QP everywhere. So we would like an integral version of that, okay? And that's the idea. So that's a very clean statement, and it gives you sort of hope. And in the theory of quadratic forms, when Siegel was originally developing this, his prototype was say, oh, we've got this Hasse-Minkowski thing over Q. What can we do over Z to sort of express this? Right? Okay. So Siegel is a mathematician in the 30s. He invented Siegel modular forms and a lot of other really cool things. But he did a lot for the arithmetic of quadratic forms. So I just want to talk about that and his specific local global principle here. So here's a fancy formula that says something. So I just want to talk about what it says. So on the right-hand side, we have a weighted average of representation numbers. Okay, so this R sub Q of M is the number of ways of representing M as the quadratic form Q. Okay? And then for every quadratic form, you can ask how many automorphisms it has. If it's positive, definitely there's finitely many. And so that's what I'm dividing by there. And this, I'm summing over all classes of quadratic forms. And I didn't say this explicitly enough. Certainly a formal proof would not allow me to say this. But all classes of quadratic forms which look locally like the quadratic form I'm given. Okay? So locally equivalent, okay, in the sense that we described before. And that's called a genus. I don't want to put too much notation, but that's kind of the main object here. So what he says is that if you take this sort of automorphism weighted average of the representation numbers for all things that locally look the same, turns out that's something you can describe locally. Okay? So this is an explicit local global principle for quadratic forms. Make sense? Okay. So the right-hand side is the weighted average of representation numbers. And this is a finite set, by the way, that I'm summing over a finite sum here. No convergence issues. That's a theorem. And then the left-hand side is a product of these things called local densities. And the idea behind a local density, and I'll define it in a minute, is that it gives kind of a p-adic measure of representation. So it's like maybe the p-adic volume of the inverse image of this quadratic, of the number under the quadratic map. Okay? And so it gives you kind of a sense of measuring how many solutions there are, because it's a measure on the level set.
What's ZV for the infinite place?
What is ZV?
Yeah.
Oh, it's R. Yeah, exactly. So V is a prime number or infinity. And if it's a prime number, then ZP and QP are different. And if it's infinity, then they're the same. Yep, exactly. So it just lets you write things in a slightly more uniform way. Okay, so the conclusion, if you look at this, is that it tells you specifically, and I guess maybe you have to prove one little thing about this product never vanishing unless one of the factors vanishes, but it gives you an explicit statement about a local global principle. Okay? So it tells you that if you have a number which is locally represented everywhere by a quadratic form, then that means that these beta v, qv's are all non-zero. Okay? And if you multiply them together, you'll get a non-zero number. Okay? That's a theorem also. And then that means that there must be some term here, some end that's non-zero, which means there must be some integral solution. Okay? And so this formula embodies a lot of cool things, not only to give you a local global principle, but it gives you a way to measure the local global principle, okay, over the genus of the quadratic form. Yes?
But isn't it an issue that it is some Q prime that is representing M and not Q that we are interested in the beginning?
That's true. Yeah. So we don't get exactly what we want. We get some integral solution, but it might not be where we started, right? And so this is the rub, right? Is that but it makes sense because locally nothing can tell the difference between these different classes, right? And so you really have no sense of where your representation is coming from. Okay? So that's exactly right. And so the challenge is if you have a quadratic form you want to understand, then you kind of like get this bundle of quadratic forms back, finitely many that this is sort of sitting in. And your life works really well when there's only one thing in that bundle. Okay, and that's the class number 1 statement. Okay. Does that make sense?
John, just for the next time you use the slides, you've got left and right switch, left-hand side and right-hand side.
Did I get my left and right switched? Okay. I do that in real life too. I'm sorry. Thank you. Okay, appreciate it.
It's his left and his right, so
Thank you. I appreciate that. No, I do make this mistake. So. Okay, thank you. So anyway, this is our main tool, right? So if we can really milk this, if we can really use this, we can understand local global types of properties and maybe get a handle on the actual quadratic form we started with, because now we've ended up sort of somewhere else. Okay. So the main tool that we're going to use to do this is that the quadratic forms are really amazing objects. Not only are they quadratic, so they do not too hard, small degree, right? So you feel like you're not scared of them, but they also have an incredible number of symmetries. Okay, and the symmetries are encapsulated in the generating function. And so if you look at the sort of the number of ways that each value is represented, so I've used this notation prematurely, I guess. The number of representations, then you can put these together in a generating series, right? And that generating series is it's just a power series, and I'm putting the numbers in like you expect, right? Like you would tell your undergraduates to do. They were a combinatorics class. But you're doing this funny thing where you're taking the powers to be powers of q, and q is e to the 2 pi I. It should be 2 pi I z. Okay, so it's q to the m. Should put the m in there. Okay, so this is a Fourier series. This is the Fourier generating series of the quadratic form, and this generating function is a well-defined function on the complex upper half plane because the quadratic form grows, the representation numbers grow polynomially, and so the it converges, you can prove, to a holomorphic function on the upper half plane. And more than that, it has a lot of symmetries. Okay? And the symmetries come from the Poisson summation formula fundamentally, but we package them nowadays by saying that the theta function is a modular form. Okay? And so modular forms are really, really useful objects for lots of reasons. We talked about, you heard Fermat's last theorem come up, the proof of that, lots of other things as well. But from the perspective of this talk, we really care that theta functions are modular forms. So modular forms have this transformation property for those who haven't seen them. If you have it, of course, just being redundant, but I'm not going to use this in any way, except to tell you that that's what it is for some finite index subgroup gamma naught event of SL2Z. The important things is that the space of modular forms for a given set of invariants appearing in that transformation law, the k, the n, and the chi, there's a finite dimensional space of them. Okay? And so if you want to do something with a given quadratic form, you're going to end up in a given space of modular forms, and you want to do something explicit there, because you care about the actual answer, right, for this form, not in general. And so one thing you can notice from this by the transformation 1101 is that it's invariant under translation by 1, your modular forms. Okay, so they all have a Fourier expansion and can be written like this. And so, again, with the m not in the q. And so what you really want to do is to sort of be able to compute in this space. Okay, and so that's kind of where the proof happens. So you compute this finite dimensional complex vector space somehow, and there are techniques to do this using modular symbols. Generally speaking. And you also want to have any structure on this space. You want to try to understand your question in terms of it. Okay? So one really important thing is that the space of modular forms always decomposes as a sum of things that come from, that take values at the cusps, non-zero values at the cusps, called Eisenstein series, or the space of Eisenstein series, and an orthogonal complement of that, which is the space of cusp forms, the functions that vanish on the cusps. Okay. So these are just sort of structures in the land of modular forms, nothing fancy about them, but that's where we are, so we want to get familiar with what we're doing. Okay? And of course, the important part here, why am I telling you all this, is because the theta series that we care about, that has our fundamental question embedded in it, is a function on this space. Okay? Cool. All right, so what we really want to do is to understand the theta series coefficients. And the main thing from the theory of modular forms that you can leverage here, which is again an extension of the types of things you see in the circle method, but made much more precise here because you have this modularity that allows you to really control what the error term is in a fundamental way, is that the Eisenstein series and the cusp forms, this decomposition here in terms of two different pieces, the functions that live on those different pieces, they have different asymptotics for their Fourier expansions. And that's kind of how you understand what this question is doing. You can sort of think about the main term in the circle method is coming from the Eisenstein part, and the error term is coming from the cusp part. Okay? And whereas in sort of analytic number theory, it's often very hard to control the error terms exactly, here we really can, okay? Because it sits in this finite dimensional vector space that you can really pin down. Okay, and you can compute. All right, any questions so far? Okay, yeah, cool. So with this observation, what we want to do is we want to take our theta series and we want to say, well, gosh, what's the part of it that's growing quickly? What's the part of it that's growing slowly? And then we can try to understand those pieces separately. Okay, so we can decompose our theta series of vector in the space along this direct sum. Okay, and so what this does is it gives you a way to decompose your representation numbers, which a priori were just numbers, into two pieces. Okay, and these pieces are an Eisenstein part and a cuspidal part. And I'll tell you sort of now, sort of for free. I should say it later, but I'll say it now. That these are rational numbers. Okay, so we start out with the representation number, which is an integer. Okay, and this decomposes as a sum of two rational numbers. Is what it's saying. Okay, that's what you get. Okay, so in the language of theorem proving, my tactic or strategy for doing this is that I would like to be able to find an explicit bound where I can say after this bound, the Eisenstein series is larger than the cusp form part. Okay? So if I can show that bound, then that means that after that point, the Eisenstein series will win in this asymptotic, and so I'll have representations. Okay? And until that happens, I don't know what's happening, but I can just compute that, right? It's finitely many things. Okay? And so that's the idea.
What weight Siegel forms going to be?
Weight 2.
All of
Yeah, that's a great question. So I should have said that. So
you only need to prove the Veil conjectures and not the Ramanujan.
That's right. You can do this. I mean, you can do this in any space, but the place where you can do it for any form it's true. The weight here, the k, is n over 2. It's always n over 2. Okay. And so if your form is odd dimensional, then it's a half-integral weight modular form, and you have to deal with all the joy of half-integral weight modular forms, which is a little bit hairier of a theory. So the nice thing is that when you think about why you have such a nice answer for the sum of, I won't go back to the slides, it takes too long, but remember the answer for the sum of 3 squares and the sum of 4 squares? The sum of 3 squares is a lot more complicated. Sum of 4 squares is a little bit less complicated. Okay? So one of the reasons for that is that the sum of 3 squares is 3 squares, and 3 is an odd number. Okay? And odd dimensional quadratic forms are harder than even dimensional quadratic forms because the theory of modular forms or half-integral weight is a much more subtle theory. It lives on a double cover of the symplectic group. Okay. So that's the idea. Okay, cool. So anyway, so going on with our tactics, so we really want to execute this to prove this kind of a theorem. Okay, so let's see what we can do. Okay, so the tactic has 3 parts. Okay, so there's an Eisenstein part, there's a Cusp part, and then there's an enumeration part. Okay, so I'll also go through each of them separately so you can sort of see the structure of this. So the Eisenstein part is I'd like to find a lower bound for this Eisenstein coefficients in this decomposition. Okay. Now, another amazing thing that Siegel did, he also worked in modular forms a lot. Yeah?
So how is the dimension of the quadratic form reflected in Theta series? So the coefficient of Theta series is only the representation of this, which doesn't have the correct dimension.
It sort of, well, I mean, it sort of does, right? Because the Theta series lives in a space with certain symmetries, right? And so the space is this space of modular forms with weight, level, and character. Okay? So the weight is always half the dimension of the quadratic form. And the asymptotics of the growth of the, I mean, just on the quadratic form side, you can see I have an n-dimensional space back into a one-dimensional space. The average size of the pre-image, it has a certain size, right? And so that's kind of the idea, is you can see it in the asymptotics of the coefficients, but not each individual coefficient. Yeah, yeah, great. Cool, so we'd like to understand this main term here, the Eisenstein coefficients. And a priori, we have no way to do that, except that Siegel gives us a way, okay? So this local global principle from before, not only is it a statement about classes and local densities, it's also a statement about the Eisenstein coefficients themselves. Okay, so he gives you an actual formula that says the Eisenstein coefficients in the theta series, that piece of it, is given by purely local data. Okay. So you can see that here. So it's given as, in both of these ways, this formula also is the mth coefficient of the Eisenstein series. So a lot of consequences for this arithmetically. The first is that you'll notice it's a weighted average of numbers, right, counting things. And so that means that this Eisenstein coefficient is always non-negative. Yeah?
Just I'm curious, is this the way you prove that equality that you showed earlier by computing in 2 different ways this Eisenstein coefficient, and then you get as a quadratic equality? Or?
That's a good question. I think that's how Siegel originally did it. Yes, kind of an unwinding argument, but it's part of. There are lots of ways to do this. It's part of the Siegel-Veil formula as well, or looking at cosets of a group. So I'm not sure to answer your question, but yeah, it's in the mix there. Yeah. Okay. So what this tells us is that this number, this Eisenstein coefficient, is a priori non-negative, right? And it's also a rational number because this is a finite sum. Okay. So that's good. So once you know that, you can sort of forget about this. And now you know you have a product of local densities that gives you local information that gives you this coefficient. Okay? Now this is a great thing, right? Because this gives you a direct handle on the main term. If you can just compute all of these local representation densities, you can explicitly compute the main term, and you can sort of really look at it and say, what's the best lower bound I can give for how this grows?
Sorry, earlier you had the same formula, right, before the representation.
I had the same formula, but I think I just didn't have the AEQ, AI's Q. So yeah, I covered, if you cover up the first part, I think it's the same formula. So I'm giving a magical, amazing second consequence of that formula. Yeah, yeah. So that's kind of the idea. If you want to understand this, you need to compute those. Okay? And So you can see this coefficient is 0 exactly when Q is not locally represented. I mean, Q at some place, right? Because it's going to be a product with a 0 in it somewhere, so you're going to get a 0. So the Eisenstein coefficient, you can look at it and visibly see local conditions for representability. Right? That's pretty cool. Yeah. Yeah, thank you. M is not locally represented by Q everywhere. Yes, thank you. Okay, great. Awesome. So if you do this, you can get a bound that sort of looks like this. It's a little bit more complicated, but for the moment, let me just sort of say that the Eisenstein bound is less than or equal to a constant times the isotropic part of the number. So the part away from this finite set of primes that you can't keep multiplying in to make the bound get bigger. Okay. So that's the theory. It turns out this is the right formula, or something like this is simple for 5 or more variables. For 4 variables, there's actually this extra little annoying factor that grows kind of logarithmically, which takes your power down by a logarithmic factor. But it really doesn't affect very much. It's just sort of there and involves the invariance that you have. Okay. So this is an explicit bound, and the idea here is whatever the formula is, this CQIs, this is a number, right? A number that you have that you compute. Okay? This is an explicit lower bound for how big your main term is going to be. Okay? And because this comes from local computations, you can control and understand every part of it. So you understand exactly how it moves as you move m and all those things. Okay? And you can do that in terms of sort of the geometry of the sort of the residual quadratic form at every prime. Okay. All right, cool. So these local densities are kind of the thing you need to compute. So I'm just going to very quickly say something about them. How are we doing for time?
10 minutes, 15 minutes.
Okay, great. Okay. So I'm going to sort of fly through this. I'm not going to really say anything. If people want to ask me, I can come back to it later. But basically, you have to do something with sort of the local quadratic form integrally. You normalize it in a certain way, and you divide out by powers of p whenever you can. Okay. And so the idea is that you want to be able to reduce each term in the way you break up your quadratic form as a direct sum. So you can use, it says Hansel's lemma, but it's Hensel's lemma. Okay, sorry about that. And that'll allow you to sort of compute the p-adic volume. Okay, so with these different pieces. So when Hensel's lemma applies, you can do a lifting all the way p-adically up. Okay, there's no obstructions. Okay. So that's the idea. And each of these local densities, the definition of it, just so you're aware, it's again, like I said, the inverse. It's the volume of the inverse image of your point divided by sort of the volume of your point. Okay, so you take a little neighborhood around and you shrink it, and that's what happens. And p-adically, this just counts the sort of number of representations mod powers of p as you go up the tower. All right, and that eventually stabilizes when you divide by sort of the expected number of representations. That's the idea of it. Right? All right, so I'm going to sort of fly by for time. So the second part is you have to understand the Cusp form upper bounds. So this is to make it effective. You need to know this can't get too big, right? Cusp forms can be understood generally in terms of the Hecke algebra acting on the space of Cusp forms. For people who've done things with quadratic forms, there are numbers that control this with the Hecke eigenvalues at the primes in particular. Here I did it for any number prime to the level, but it could be any primes in particular. And for the primes, because of the Weil conjectures for weight 2 modular forms, you know that these eigenvalues in absolute value are no bigger than 2 root p at the primes. And this is really important because this gives you a very, very sharp control over the error. Okay? And so it means that the main term is growing like m, the error term is growing like square root of m, and so eventually if m gets large enough, you'll win. And it's just a matter of formalizing exactly what that means. Okay? And it can be a little complicated, but this is kind of the bound you would get, that the Eisenstein coefficients is less than the a divisor function square root of m times something to do with the coefficients of how the form is sits in the space of normalized Hecke eigenforms. Okay? So again, the important part here is not all the letters. It's that this is a concrete upper bound for the cuspidal coefficients in terms of stuff that you compute and stuff that you know. Okay? Now this computation is a computation in the space of modular forms, which could have, depending on what your form is, very high dimension. It could be defined over a number field of very large degree. It could be sort of an irreducible module over that number field. So there's a lot of stuff that goes into this calculation. It can take a long time. Magma can crash many, many times on you. And so it depends on the form you're looking at as to whether you can do this. But if you can, then you get it bound. Okay, cool. So part 3 is the exciting part. Now I just have finitely many, very, very many, finitely many things. And I need to just check that since they don't meet the bound, they're not represented. Or they are represented, or whatever the condition is. That's a great question. So in this case, I'll put it at the end, but you have to check numbers up to about 2 times 10 to the 11th, 10 to the 11th, 10 to the 12th. And they come from square classes where you have a certain number of maybe 12,000 primes in it, and you make square classes and see if they meet the bound. So you have to have an algorithm to be able to put these together and check quickly. And then also, I'm checking a theta series. Is a number represented? If I give you a number like around, with 10, 11 digits, and I say, does this quadratic form represent it? Tell me now, right? How do you do that? That's not so easy, right? You've got to enumerate up to that point, and that's kind of computationally too hard. So there's some tricks to do this, where you look at a subform that's ternary, and you look at a cylinder and compute just if something's represented or not on that in some tricky way. Okay, so there are ways to make this computation better, but I'm not going to talk about them because we don't have time. So
are these all real number computations that you would try to do if you wanted to do it verified with interval?
Yeah, these are integer computations. So this is why I really plug a vector into this quadratic form, and I see what number comes out, and I say, oh, is that what I wanted? No, exactly. So you keep track of that. And so you have to enumerate this sort of set of possibilities, prime by prime. Like you have to find some subform, a ternary subform that sort of allows you to do this more quickly. And so here, again, so Kevin, to your question, it's a lot of numbers to check, millions of numbers, but they're spread out over, in a very thin way because the set of prime divisors is constrained. Okay, cool. So that's kind of the idea, and if you could do all these steps, then you can prove that this quadratic form represents everything except for 2 and 22. Okay, so that's the way you would do it in general. And the great thing about this technique, and I made the technique, so I'm excited about it. Of course, I'm biased, but I still think it's great. Is that it allows you to answer the question of what number is represented by a 4-variable quadratic form, positive, definite, integer valued, for any quadratic form. There's no class number restrictions here. It's not can I do it. It's can I afford to do it given the compute resources and the technology and who wrote my software, right? So this kind of answers in an algorithmic way the question. Okay, so I think that's kind of cool. And lets you can do other things sort of with confidence. Okay? So in order to do this, obviously I didn't do it by hand. Right? I had to write some libraries to do this. And so I wrote a lot of code. So I tried to understand this calculation. Once I prove the theorem, I need to implement sort of how do I compute all this stuff, right? And so in particular, the local densities took a long time, and it was my first sort of large programming project. So around 2007, I made some code that really computes all of these local densities and checks that they work correctly, a lot of unit tests and things like that. I use this to do other things. I also wrote a quadratic form class in Sage, so that was to try to, as a first step to put this code into Sage. So if you use that, then I'm happy to answer your questions about it. And then in order to do the modular forms computations, it's very hard to find something that could really do this at scale. And so Magma was sort of the thing that I used eventually. PeriGP also now supports modular forms. But this computation is a beast. You have to compute eigenforms in some space of modular forms you don't know a priori is going to be small. And there's no reason to expect it to be defined over a small number field because you have an operator acting. It's rationally overall, but the eigenforms are not necessarily defined over Q. They're defined over maybe a field of the dimension of the space with one orbit. So that's some extra code to be able to do that in Magma, and then also to be able to compute the bound from it.
And again, are these symbolic computations?
This is a good question. So the Magma has a modular forms object that it makes, okay, and that's defined over Q. When it goes to find the Hecke eigenvalues, it defines an internal number field object, okay, which may or may not be represented in a way that has small coefficients. I mean, the coefficients can be screens long, right? And so it's crazy, okay? And then once I do that, I want to be able to embed that into the real numbers to get a number, right? And so here there's a possible precision loss because I compute it to as many digits as I can, and then I embed it into the real numbers, and then I sort of add 1 to account for rounding, but not in a provable way, right? So I can't control what Magma does, and so this is a place I get nervous. And if I had more time, I'd talk about what is a proof, because I still don't quite know, because you can always have a mistake somewhere, a cosmic ray hits your computer and you miss a case, and I mean, who knows, right? So you kind of do your best here, but this is a place I really couldn't do my best because I couldn't get into the internals. So you really want to implement this yourself. And the code that I'm talking about here is all available on my website, my GitHub website. So, and I'm currently working on getting this sort of more together in my free time. So things I want to ask people here are, can this possibly, maybe, be a formal proof one day? I don't know. So here are some things I wonder about. So I saw Kevin's name attached to this, so I bothered him yesterday about modular forms in Lean. Okay, so here you want to be able to define the space and also the Hecke action and the eigenvalues and all the good stuff that we just talked about. Okay, you need to be able to define the sort of Eisenstein Cusp form decomposition of modular form spaces, which is a canonical decomposition. Okay. You have to know the theta series is a modular form, which is a Poisson summation type of proof. The Siegel product formula is it's a sort of simpler manifestation of the Siegel-Weyl formula. So that involves understanding modular forms essentially also. You need to know this sort of sharp bound on Hecke eigenvalues, which is the Weyl conjectures. So that's an ingredient to this. Okay, to allow it to
Abelian varieties.
say again.
I mean, that's the hardest part by far, theoretically. You need
Okay.
the Weyl conjectures for abelian varieties.
Yep.
So we'll need a Tal cohomology, probably.
This is just weight 2, right? Okay. And then there's like all the code that you write about this where it could always be a mistake, right? And so it'd be nice if there's a way to certify these algorithms to prove that they would work and the implementations give the correct answers, right? And so there's lots of algorithms there involved with it. So that's kind of what I want to talk about today. It would be great if there was some proof algorithm to determine this, and it could be formally verified, and I would love to connect with anybody who's interested. So please feel free to reach out, and happy to chat with you. That's all. Thanks for listening. Really appreciate it.